Hello friends, now we will discuss the full wave rectifier using operational amplifier. This is the circuit diagram of a full wave rectifier using op-amp. Say this is op-amp 1, this is op-amp 2, right? So we will see the operation of this circuit as full wave rectifier. First we will be taking case 1, that is positive half cycle, right? So positive half cycle of what? Positive half cycle of input voltage. During the positive half cycle of input voltage, let us see what will be the equivalent circuit. When input voltage is positive, so this is connected in inverting mode, so this voltage at this point, which is nothing but V01, output voltage of op-amp 1, becomes negative. When input voltage is positive, because of the input at inverting terminal, this voltage becomes positive, right? This voltage becomes negative. When input is positive, this voltage becomes negative. So when this voltage is negative, the diode D1 will be on and diode D2 is off, because it is reverse bias, it is forward bias. This is the equivalent circuit. So during positive half cycle, D1 is on and D2 is off. That's it. So when this is off, this will be the equivalent circuit. Now let us see this circuit carefully. Say this is node A. So voltage VA, voltage at node A is voltage at node B. Say this is node B. For ideal op-amp, voltage at inverting terminal is same as voltage at non-inverting terminal. So voltage at node A will be equal to voltage at node B, and voltage at node B is 0, so this becomes 0. So voltage at this node A is 0. Fine. Now I have to find, so if this is 0, so there is no current here because this is grounded. So when it is grounded, why there is no current? Because current in inverting and non-inverting terminals is 0 in ideal op-amp. If current here is 0, so if current here is 0, this is open, so if it is 0, so whatever is potential here, which is 0 potential, same will be potential at this point. So this is C, this is D. Fine. So voltage at this potential is 0. So if voltage at this potential is 0, so therefore now for ideal op-amp, biasing current entering into inverting and non-inverting terminals is 0. So voltage at node D will be same as voltage at node A, and that is 0. So that means this is at potential 0. Fine. Now see it carefully. What will be the voltage at node, say this is E node, or you can say V01. Fine. So now if you apply KCL at node A, KCL at node A, what do we get? 0 minus V in by R plus 0 minus V01 by R, and that is equal to 0. You can take it like that. So what will be V01? V01 will be equal to minus V in. V01 will be equal to minus V in. So voltage at this is minus V in. Now this is node C. So apply KCL at node C. KCL at node C. So what will be when you apply KCL at node C? So voltage at node C is 0. We have already seen from here. Voltage at node, for ideal op-amp, voltage at inverting terminal is same as voltage at non-inverting terminal. So VD is 0, so VC will be 0. So 0 minus V01 by R plus 0 minus V0 by R, and that is equal to 0. So this gives the output voltage equal to minus V01. And you know what is V01? V01 is minus V in, so that is equal to minus of minus V in. So that means output voltage is equal to same as input voltage during positive half cycle of input voltage. So output voltage is same as input voltage during positive half cycle of input voltage. I hope concept is clear. So what we did, we have taken this potential to be 0 because for ideal op-amp this is 0, for this will be 0. So for ideal op-amp, current in inverting, non-inverting and inverting terminal biasing current is 0. So current in this path is 0. This is open. So if current in this path is 0, so whatever is potential here, same is here. Again, the same will be potential here for ideal op-amp. So what we did, we applied KCL here, we applied KCL here, and we could find output voltage. Fine. So for positive half cycle, output voltage is same as the input voltage. Now case 2. Let us talk about negative half cycle, right? So for negative half cycle, this is negative, so this becomes positive. This point becomes positive because it is connected in inverting mode. So when it is negative, so it will be positive. In that case, diode D1, which was like this, it will be reverse biased, right? So it will be reverse biased, and diode D2 will be forward biased. So diode D1 will be off and it will be on. Forward bias diode means on, short circuit, and reverse bias diode means off, means open circuit. So this becomes the equivalent circuit for negative half cycle, right? Now let us see it carefully. This voltage is V01 now, right? Voltage here is V01. Voltage at this potential, first of all, for ideal op-amp, voltage at node A will be same as voltage at node B. So voltage at node A is 0. So voltage at node A is 0. Now, what will be voltage at node D? We don't know, right? There will be some voltage at node D. So definitely that voltage will be equal to V01. Why? Because for ideal op-amp, current entering into inverting terminal is what? That's 0, right? So current entering into inverting terminal is 0. So that means current entering into inverting terminals is 0 for ideal op-amp. So whatever is voltage here, so VD will be equal to V01. But in some textbooks, you will find this resistance is not there. That is also correct. Fine. So in fact, in our text, this will be 0. If it is present, this will not make any difference to the circuit. So whether it is present or not present, because current entering into non-inverting terminal of op-amp or biasing current of op-amp is 0. So if it is present, even then this voltage is same as this voltage. If it is absent, even then this voltage is same as this voltage. So presence of this resistance won't make any difference, right? Now, so that's why I have removed this circuit, because I have not taken in textbook. So that's why I have removed it. Fine. Now let us see. So voltage at node C. Remember, voltage at node C, VC, will be equal to VD, and that is equal to what? V01, right? That is V01. Out voltage at node C is equal to the voltage, output voltage of op-amp 1, that is first op-amp, right? Now if you apply KCL at node C, let us see what will happen. Now by applying KCL at node C, I get now KCL at node C, right? That gives what? VC minus, what is voltage VA? VC minus VA divided by 2R plus VC minus V0 divided by R is equal to 0. What is voltage VA? Voltage VA is same as voltage at node B, and that is 0. Voltage at this node is same as this voltage for ideal op-amp. This voltage is 0, so VA is 0. So I can simply write 0 here at this point. Fine. So that gives me the voltage V0, and we know what is VC, that is V01. So this is V01 upon 2R plus V01 minus V0 by R is equal to 0. I repeat, because your VC is same as V01, I have replaced VC by V01 here. So that gives V01 or V0 equal to, what will be V0? V0 will be equal to 3 by 2 into V01. That is your output in terms of this voltage V01. Fine. Now, what is the aim? My aim is to find out the relationship between output voltage and input voltage from this circuit. Fine. So let us try to find the relation further. So you just remember this expression, that is V0 is equal to 3 by 2 V01, right? That is output voltage of second op-amp in terms of output voltage of first op-amp. That's we have calculated. Now let us proceed further. Applying, now what we do, we apply KCL at node A. Here we have applied KCL at node C. So now applying KCL at node A. When you apply KCL at node A, what do you get? VA minus VN, VA minus VN upon R plus VA minus V01 upon R plus VA minus VC upon 2R, VA minus VC upon 2R. But we have seen VA is equal to VB is equal to 0 and VC is equal to VD and that is equal to V01. That's what we have seen. So this gives 0 minus V in upon R plus 0 minus V01 upon R plus 0 minus V01 upon 2R, that is equal to 0, right? So now what do we get? We get V01 in terms of V in, or this gives V in equal to what? 3 by 2 V01 with the minus sign, or this gives V01 equal to minus 2 by 3 V input. So by putting this relationship here in this equation, we get V0 equal to, you put V01 this, so 3 by 2 into 2 by 3 input voltage with minus sign outside. So V0 will be equal to minus V in. So for negative half cycle of input voltage, V0 is equal to minus V in. It means output voltage will be inverted version of input. So during negative half cycle, output will be inverted. So output will be inverted version. It means this is inverted during the positive half cycle. So during this cycle, what was there? D1 was on, D2 was off. During this cycle, D1 is off and D2 is on, and so that's what you have. So what is the output? Output is nothing but a full wave, that is fully rectified wave, you can say. So input signal is rectified here, and we have only positive pulses at the output of second op-amp, that is output of the rectifier. Now let us see the transfer characteristic of the full wave rectifier. What is transfer characteristic? The transfer characteristic of the rectifier is nothing but your variation of output voltage with respect to variation in input voltage. So we will be seeing the variation in output voltage of the full wave rectifier as a function of input voltage. So this is V in, this is V0. So input voltage is varied from minus Vm to plus Vm. This is plus Vm, this is minus Vm, this is plus Vm. So output voltage is varying only from 0 to plus Vm here. So output voltage varies from 0 to plus Vm here. Input voltage is varying from minus Vm to plus Vm. During positive half cycle, your output voltage is same as input voltage. That is y is equal to x. That is nothing but a straight line of unity slope. That is the characteristic. This is a straight line of unity slope. For positive half cycle means when input is positive, output is positive. When input is positive, output is positive. During negative half cycle, V naught is minus V in, right? Now let us see. When input is 0, output will be 0. But when input is minus Vm, output is plus Vm. So when input is minus Vm, output is plus Vm. And you connect origin with this point. So that gives the variation of output voltage during negative half cycle of input voltage. So this is the characteristic of full wave, that is transfer characteristic of full wave rectifier. Fine. So I hope the concept is clear. Now, sometimes in GATE, especially in GATE exam or in some exams, your full wave rectifier may be obtained by using the two half wave rectifiers, right? So I may be using two half wave rectifiers to implement a full wave rectifier. Let us see how it is possible. Fine. We will try to analyze rather than talking about, that's purely from examination point of view. There are some questions in GATE exam where you may be finding, or you may have to find the characteristic of a given circuit, or you may have to identify a circuit by simply identifying the characteristic, right? Now let us see carefully. We know what are the characteristics of full wave rectifier. This is output, this is input, and these are the characteristics. We have just seen this is plus Vm, this is plus Vm, this is minus Vm. These are the characteristics, right? So during negative half cycle, it is reversed. During positive half cycle, it goes as it is. There is no inversion. So now, let us take a circuit. This is simple circuit, right? So I have to find the output of this circuit. I have to implement this characteristic, right? I have to obtain the characteristic similar to this by using half wave rectifiers, right? So if you remember, in half wave rectifiers, one is the half wave rectifier where the output is same as during positive half cycle. Output is what I need to do is, during positive half cycle, output should be same as input. So I have to use one half wave circuit where output is same as input during positive half cycle, right? So it means, let us see carefully. Suppose I have this circuit, I have this circuit, right? Again, what I do, I connect one more resistance here, right? And this is grounded. This is minus, this is plus, right? And here, what we do, we connect one half wave rectifier, right? And here we connect another half wave rectifier, right? Like this. Fine. Now, and both of these are connected to input. This is P, this is Q. These are half wave rectifiers, right? This is half wave rectifier, right? Fine. Now this is R, this is R, this is also R, right? So for this, for P, suppose I select P like this. Suppose we have, in this case, I select a filter which has characteristic like this, right? I have the filter which has characteristic like this, or I may be having a filter which is having characteristic like this, right? So I select a filter having characteristic like this. So when it comes here, your input, this will be inverted. This input will be inverted. So output of this filter becomes positive. So output of this filter becomes positive like this. Output will be basically the signal. If it was negative here, it becomes positive. I select filter like that. Fine. Similarly, I may be selecting a filter here which was having characteristic like this, right? So if I have filter, this filter Q having characteristic like this, when it reaches here, that has characteristic like this. And this way, by selecting P, so what should be the characteristics of P? The characteristics of P could be like this, right? That means what? That means when input voltage is positive, output voltage is negative. Just inversion of your input voltage, right? And during negative half cycle, it is 0. So I have a half wave rectifier, maybe this, maybe this. Another way, another half wave rectifier has to be like this. When input voltage is negative, this becomes positive. So by using this concept, I can get the characteristic and the output like this. We will see some questions based on this concept. By selecting proper half-wave rectifiers, by selecting proper characteristics of half-wave rectifiers, I can implement a full-wave rectifier. That is what I am trying to say. But we will see examples which appeared in exam, and it will be more clear from those examples, right? So wait for examples we will be discussing now. Now let us see the example based on full wave rectifier. Here the example is basically relating to the implementation of full wave rectifier using two half wave rectifiers. So let us see the example. The block diagram of two types of half wave rectifiers are shown in the figure. We are given the characteristics of these two rectifiers. The transfer characteristics of rectifiers are as shown in the block. It is desired to make full wave rectifier using half wave rectifier. The resultant circuit will be. First of all, before you implement a full wave rectifier using these two rectifiers, these two half wave rectifiers having characteristics like this, you should be knowing what are the characteristics of full wave rectifier. So I'll draw the characteristics of a full wave rectifier first, and then we will see how to implement that. So x-axis is input voltage and y-axis is the output voltage. And now if you see the characteristics of full wave rectifier are like this. These are the characteristics of a full wave rectifier. You can refer the video on this. I have just shown you that, right? So this is one half. For negative half of the voltage, output is positive, and this is second half. So for positive voltage, output is positive. So this is a characteristic of one half wave rectifier. This is a characteristic of another half wave rectifier. Now if you match these characteristics, the characteristic of this rectifier Q is same as this part, right? So without inversion, we can directly get this part of the characteristics from this. You can see both are matching with each other. But here if I invert this characteristics this side, I will be able to implement that second part, right? So I need to perform inversion of operation on the halfway rectifier P, and there is no need to perform inversion operation on Q. So that means Q has to be connected at non-inverting terminal and P has to be connected at inverting terminal. So now let us see the option. In this circuit, P is connected at non-inverting inverting terminal. Q is also connected at inverting. Both are connected at inverting terminal. So this cannot be the option. Now come here. P is connected at inverting terminal, which is a requirement, and Q is connected at non-inverting terminal, which is a requirement. So this should be the answer. Let us see this also. Here Q is connected at inverting terminal, which is not a requirement. So this cannot be the answer. Here P is connected at inverting, Q is connected at non-inverting, Q is both are connected at non-inverting terminal. This is not the requirement. So B should be the answer. So now let us see the answer. So answer is B here, and remaining part is just an explanation. So that finishes your the question on full wave rectifier. You don't have many questions, but this is important from examination point of view, because there are questions in the past which appeared on the implementation of a full wave rectifier using the half wave rectifiers. So concept should be clear. Fine. So and that finishes your rectifiers.